15.4 in my lab statistics wasn't as hard as the 15.3, so
That's good to hear. Was it because of, I remember 15.3 had really gnarly like concept questions after you did the
Yep.
main interval. Was there less that in 15.4?
yeah, it just asked you like if the independence was met
Mm-hmm.
or if it wasn't met. And then if you, there was another, I can't remember exactly what it said, but then if you could assume that the something would work. I
Mm-hmm.
can't remember.
Probably
It just had three,
central limit theorem, maybe.
but it just had three drop down boxes and you would just select the best answer, and it was the same three for all the questions.
Awesome. That's good to hear. Yeah, I try to pick questions for that section where it wasn't anything weird going on. The assumptions are just generically met on each one of them.
Yeah, it wasn't brain bleeding.
Yeah, that's good to hear. That's a good way to say it. Well, quiz 11 was on the 15.3 hypothesis test problem. And the section you're mentioning, that's 15.4, forgetting the section numbers already. That's the quiz that we didn't quite get to. That would have been quiz 12 if we could collect a quiz, but collecting homework over finals week is usually considered a really bad call. So instead, we'll just have sample problems we'll look into here. And there's also the real final exam you can take a look at into here as well for some similar questions. But welcome back, folks. Our goal is really to just push forward on the final exam review. We started the first question and almost finished it. And so we'll probably get through quite a bit more today. Next class will just be the same thing, finishing off the work here on this document. But any other questions or comments at all, folks, before we get started? Okay, I want to mention one more time, the math department did something that's kind of painful for me, but we just, the math department is my boss, so when they say jump, I ask how high. They've changed two of the questions on the final exams that I wrote. Well, this is the one from fall 2024. And this is the effect that they made for the change. They took a question like this, doing a hypothesis test, and they wrote the question. So they just said, perform a hypothesis test using some significance level. And that's tough because that's a lot of white space. I mean, for me, when I try to do these kind of problems, I like to keep it kind of on the rails. The actual solutions to this final exam shows you how I actually wrote those same exact questions. It really looked like this. And parts A, B, C, D, E, and so on just sort of keeps us on a train track of what should we do next. Without all that, this question gets a little bit harder. And that's the major thing that we were discussing in our final exam review questions. I rewrote these questions here to make it look like the real final exam so that we're really practicing at the level that we're going to see these questions. There's just going to be two questions like these that the math department wrote. Everything else is written by me and same kind of instructions that we're seeing. So if we don't have a parts A, B, C through say like part F, we can still have it on our notes. So I'm going to write out careful steps on every single one. The thing that I would do next, doing a complete analysis for these kinds of data. So this problem was about successes where out of a national sample of 2,260 Americans, 1,288 indicate they would prefer to live in a hot climate. So in yellow, it's the alternative hypothesis. We're looking for evidence that a majority of, so more than, right tail test, 50%, prefer to live in a warm climate. And that's why the alternative hypothesis looks like this. HA is that P is greater than 0.50. And P is going to be the true proportion of all Americans who prefer to live in a hot climate among, I guess that's redundant, USA citizens. So we went through the mechanics of the test. We're skipping the condition checking and just going through the main parts. The next thing, after getting the test statistic Z, calculating the standard error, is just to compute the p-value. But this is a pretty fast computation once we've got some good practice on this. For the p-value, first thing to link up in our minds is if you see Z, it's because the data is categorical. That's why there's a parameter P here, and we say proportion. Z reminds you that this is all done in the standard normal distribution. N01, which means we're using normal CDF in the calculator. Next thing we do, just put down a 0 if you prefer as a base point. The test statistic 6.6460 should be plotted on this curve. That's really challenging to plot because it's clear over here. It's not exactly even right. It's probably much further to the right, but I'll just put it here so it's not too far out there. So here's Z, 6.6460, shade to the right, which is kind of hard to do because the test statistic is so large. But that's my attempt at shading and drawing a diagram for this problem. Then the test statistic Z is input 1, lower. We are shading to the right, even though it's kind of hard to see in this problem, but that's input 2, upper, 10 power 99. So the p-value is just a generic back in chapter 5 problem, finding the area under this curve. So back to the calculator, hit second vars, go to normal CDF, put in the test statistic first, 6.6460. Upper values 10 to the power 99. Parameters are 0, 1. So calculator should be set up like this. I think we mentioned before, we're expecting a small test statistic. Probably going to come out in scientific notation, but let's see what happens. Yeah, definitely scientific notation on that. If you got something like this on a real exam setting, that can be kind of discomforting. It doesn't come up a lot in the homework. I think once or maybe twice you get something like this. So here's what you would want to write down if you saw this in your calculator. The p-value is equal to 1.513. E power negative 11 just means times 10 to the power negative 11. That means the decimal point right here moves left 11 places. But rounding to 4 decimal places is common for these kind of problems. So probably the easiest way to write down the p-value is the p-value is 0.1234. Then go an entire whopping 7 more places, and then 1513 starts to show up. But there's the p-value rounded down to 4 decimal places, just as effectively a 0. Does that make sense to folks on what we got for this weird output here? Okay, I can't guarantee that will come up again on the exam, but if it does, it's not an error. Really, this is what you have, effectively 0 for your p-value. That means as far as alpha goes, we're going to be rejecting the null hypothesis. So let's put down this comment here. This is less than 0.05, which is equal to alpha. So we will reject H naught. Well, this is just a third step. So there's not really like a part D where it said find the p-value. But the emphasis to step 3 was this. So I'll put it in a box. Getting the p-value, and then the last part was just deciding what decision will we make in our practical conclusion. So if we're rejecting the null hypothesis, that means we have significant statistical evidence in support of the alternative. In fact, we have a gargantuan amount. 6 standard deviations is a lot. If the null hypothesis were true, then this value we got on our statistic is more than 6 standard deviations away from the statement of the null hypothesis. So as a practical conclusion, though, something that makes sense to people, we'll say, first, we have found overwhelming. You don't have to say overwhelming, but I think it's good sometimes to say that this was a lot of evidence this time. We have found overwhelming statistical evidence at the 5% significance level that whatever that statement is for HA is true. It's P greater than 0.50, so we write this out essentially verbatim. The population proportion of people who prefer to live in a hot climate among all USA citizens. Okay, so we wrote out P. Here we'll just say for the alternative hypothesis is greater than and then just mention the value. If you said 50%, that'd been appropriate. It reads weird because we didn't say percent here, we said proportion. So to keep things kind of more parallel, it's probably more standard to say greater than 0.50. But no harm done if you said greater than 50%. So that's our practical conclusion. I think it confirms like about what most of us would have guessed, that people don't like being cold. But you know, if you lived in a hot climate, you might not like the humidity either. But it just depends on where you are, I guess. But for a representative sample of all USA citizens, it was greater than 50%. Well, that's the hypothesis test analysis. If this was a problem that we were really working on, say, about to publish, we would also do the confidence interval analysis to follow up on it. We'd want to estimate P through a confidence interval. But here's where the questions are going to end. It'll just be one hypothesis test, one confidence interval on the real final exam. Well, any last questions before we try out to example 2 next? Okay, example 2 is kind of an interesting one. Some people graduate in December, so this could potentially be relevant. You never know. Example 2 says, how much money do people spend on graduation gifts? Who knows? But we have a study in 2016, the National Retail Federation, I didn't even know that existed. Apparently there's a retail federation, surveyed 2,511 customers. So there's a sample size for sure in there. N equals 2,511, who reported that they bought one or more graduation gifts in 2016. So one or more, I guess some people buy a lot of them. The sample was selected to be representative of adult Americans who purchased graduation gifts in 2016. That's an important statement here. Even if we're not checking conditions on these problems, it's telling you what the population is. All Americans who purchased graduation gifts almost 10 years ago. We're told next, for this sample, the mean amount spent per gift was $53.73. So from there, because this is relating the sample, this is really a Y bar is 53.73. And they make an assumption, suppose the sample standard deviation was $20. Trying to keep the same color coding as when we did these problems from before. So for this part, this is going to be S equals $20. Okay, so they go on to say, perform a confidence interval analysis at 98% confidence, provide a practical conclusion using the context. Well, that doesn't tell us a lot from the instructions. Usually when we did this problem, we had like 5 different parts that we went through. Maybe the last thing we'll do is convert the confidence level to a decimal point as 0.98.
This would have been chapter 13.
Close. I believe this one is chapter 14, only because the data is quantitative this time. Chapter 13 was just the confidence interval for a proportion. And then chapter 14 went into confidence interval for a mean.
Yes. T-star.
Yeah, good call. This is going to be a T-star problem. Absolutely. So this one actually has a lot to do from scratch because we can't just look up a table and get the Z star, we have to compute the T star out, just like you said. It's also a tricky question like the last one because the landscape is wide open. Again, I like my problems to be kind of on the rails. That's just how my mind works. If I see this, it's kind of anxiety producing. That's a lot of white space and not a lot they're telling me to do. This will happen on the real final exam, so come prepared with notes expecting this kind of question. And here's a natural step one. Define the parameter. These data are quantitative this time. We have units, we have a sample mean, a sample standard deviation. The unit is dollars. All that information tells us that the parameter should be mu, the one I was getting mixed up with on the last problem. So for quantitative data, a parameter mu is going to be the population mean. Stating the parameter for quantitative data is its own little game. We still mention the population like before, but we also have to mention the unit to put this in context. Well, the sample mean is here. Mu is just the population mean. The unit is money. So we can say mean amount of money spent. And it might be a good idea to be slightly more specific. You could end it right here, mean amount of money spent. And then you have to mention the population. But this is all about graduation gifts. Things like, I don't know, fancy pens, a book, maybe depending on your parent, a Ferrari, who knows how wealthy you are. But this is just about graduation gifts. Noticing that the sample mean is $53.73. Looks like no one got a Ferrari in the sample of size 2,511, or else this amount would have probably been a lot bigger. So we would have almost certainly had an outlier there. But let's call this the mean amount of money spent on graduation gifts. And the sample was adult Americans who purchased graduation gifts in 2016. So we'll say among all adult Americans. And you know what? We can shorten this up a little bit and just say in 2016, because I think the context does convey these people bought the graduation gifts. But anything you can take out just to make it a little bit terser is a good idea. If it feels like it's a big part of the problem, or if it's just not implied, it might have been a good idea to say all adult Americans who purchased the graduation gifts in 2016. But if you make some tiny short adjustments like that, that's okay. You don't have to copy the problem down verbatim. Well, any questions at all, folks, getting the parameter down? Okay, notice the analysis we're doing. If it's a confidence interval, we do not define hypotheses. There's no null or alternative hypothesis here. It's purely an estimation problem this time. So now we go on to step 2. For a confidence interval problem, I would say a really good step 2 is what you were mentioning earlier. Get the critical number T star in this situation. Find T star. To get T star, we have to take a couple steps. First, we need the degrees of freedom. Degrees of freedom is going to be the sample size n reduced by 1. Sample's quite large in this problem. The National Retail Federation, I guess they have a lot of money and leverage to really look into this demographic. So it's going to be 2,511 minus 1, 2,510 altogether. After getting the degrees of freedom, the next thing I would calculate is an area, because we're using inverse t in the calculator, and that's one of the inputs it wants. But there is a really specific process every time we calculate this area in chapter 14. We took 1 minus the confidence level as a decimal, so 1 minus 0.98, divide by 2. That gives us the right area to look into. Let's put this in. 1 minus 0.98. Divide by 2. If you're a little bit faster at mental arithmetic, you might have came up with the 0.01 faster than I did. But you know, the numbers can get a little foggy if you're taking this exam between 8 and 10 p.m. So good to be accurate. 0.01 is what we get. Take both pieces of those information and we'll get T star. So we'll use inverse T distribution. So back to second vars. Inverse T is option number 4, right under inverse norm. You would use inverse norm if you're computing a Z star, but we have a whole table for common Z star values, so we often didn't do that. So for inverse T, area goes in first. Should have done that part first. 0.01 for area. Degrees of freedom, 25, 10. And that's all it is. So in your calculator, this does the job. Hit enter twice. And here's our critical number. There's always a lot of questions on what to do with the negative. In a MyLab statistics setting, we always can take the positive value, but the formula uses both. So if you stated a negative value here, it's not wrong. It's one of the two values you use. It just might seem a little weird. We almost always write down on paper the positive value. So 2.3278. The cool thing about the inverse T distribution is that was the left tail area. The right tail area is 0.99, and that's what would have given you the positive value. But using the left tail area and just taking off the negative sign always gives you the right value for the critical number. So that's a good step 2 on this so far. For step 3, this is what I would do next in a confidence interval. Compute the standard error. And the standard error you get depends on if the data is quantitative or if the data is categorical. We'll do both confidence intervals to cover all bases. For the quantitative data, we're talking about the standard error of that statistic, y bar. So it's labeled as SE y bar, and the formula is awesome. It's just S divide by the square root of sample size n. We use that both in the test statistic for hypothesis testing and in the confidence interval if it's quantitative data. So this comes up twice. So to compute it, go back up to S20, divide by square root of sample size. Here we indicate at the top, 2511. So again, I didn't say anything about rounding on this, but 4 decimal places is a great neutral assumption for these kind of problems. So let's go 20 divide by square root of 2511. So to 4 decimal places, this one comes out as 0.3991. And we're just about there. Step 4 is just to compute the whole confidence interval itself. And the 5th step is just going to be the practical conclusion. Any questions at the moment with what we've got on paper so far? Okay, let's say for step 4, if your data is quantitative, use this formula. It'll be y bar plus or minus T star multiplying standard error of y bar. So quantitative variables gives us this formula. Now we're just going to plug in what we have. For the first part, y bar, look at the top, it's going to come out as 53.73. Then plus or minus in the middle. Next is T star that we calculated. So in place of T star, look into step 2. It's a 2.3278. And then last multiplies standard error. This is all just one symbol, so we don't multiply by y bar again. I forgot to say y bar right there, just for the sake of completeness. That's a good correction to put in. So just multiply by that one number, 0.3991. This is going to give us two numbers. And from those two numbers, we have the estimates on mu, a lower bound and an upper bound. So the result of this computation, just like we did often in class, I'm going to put down here on paper. So let's start typing this in, 53, let me try again, 53.73. Subtract from that 2.3278, multiplying 0.3991. All right, let me know if I get slightly different digits from you. This is money, so at this step, it makes sense to round to the nearest cent, 2 decimal places. So $52.80. Is the lower end. Then the massive trick here in the calculator is to hit the up arrow twice, highlight so you can paste this down. The left arrow, because we're only changing this one spot that looks jarring, one spot right here, we're changing to the plus now. So overwrite that with the plus. And this will be $54.66 upon rounding. 54.66. So that's what it says about graduation gifts in the United States of America in 2016. This is a large sample and it was also representative. So there might have been some outliers in there, but looks like no one got a Maserati in this sample size, because on average for the entire population, it's between $52.80, $54.66. Nothing too impressive, but it's the thought that counts when it comes to a graduation gift. Last step is to just say what we were hinting at with what this interval is saying in words. So that's the practical conclusion. So every one of these methods is always going to end with the final step saying, give a practical conclusion. So this is the guide. If you have no parts A through F telling you how to do the conference interval, just have ready on your notes. Recall there's 2 pages of notes you can have on the final, steps 1 through 5, and that covers the same bases. So for the practical conclusion, much like with the hypothesis test, we just go to the interval we see right here. Let me temporarily highlight it. We're just reading this out verbatim without using any special symbols. It's a good idea to start in the middle first, mu. So look into step 1 where we defined it. We can say, just so we don't forget, with 98% confidence, if you said 0.98 confidence, that's okay too. It's just a change of unit. Okay, so now that we covered that base, we know how confident we are that this interval captured mu. We can say the population mean amount of money spent on graduation gifts among all Americans in 2016. Okay, we're done with that parameter mu, and we just say is between those $2 values, is between $52.80 and $54.66. So if the question on the final exam turns into a conference interval with quantitative data, this is about what it would look like. Different context, different numbers, but same process step 1 through 5. Well, we did, folks. That's our second statistical inference for the set of notes. We'll look into two more, and that'll cover any possibility for data type and procedure type on the final exam. Any last questions before we take a look into the next one? Okay, so here's our new scenario. A corporation maintains a large fleet of company cars for its salespeople. Maybe this is Papa John's, who knows? It goes on to say, to better understand the average number of miles driven per month per car, a simple random sample of 40 company cars is selected. We're told they have a large fleet, so we're assuming that's less than 10% of the entire population size. Maybe they have thousands of company cars. But we do have a random sample of n equals 40 cars in this problem. They go and just spit out some data. Sample mean. Right here, the data is quantitative. So a mu is going to come up again. And this one is just a hypothesis test, now with quantitative data. So we have a sample mean, 2,752 miles. So Y bar is 2752. And the sample standard deviation, 550 miles. So that value is for S is 550 miles. Let me put miles on both just as a reminder of the unit. Okay, so this is the context so far. A study's been done. They have a mean, they have a sample, but this is a hypothesis test. So something needs to tell us what that test will look like. Here's where the next part of the problem comes into play. Records for previous years indicates that the average number of miles driven per month per car was approximately 2,600 miles. That sounds like a hypothesized value, mu naught, when they mention that. There's a question mark here, so that's possibly the alternative hypothesis. Do these sample data provide significant statistical evidence that the average number of miles driven, let me say again, average number of miles differs from 2,600 miles? So 2,600 came up in this statement. It's absolutely the hypothesized value. And this whole statement in yellow is just the alternative hypothesis written out verbally. So this is HA, and mu naught is the 2,600 miles. Hypothesized value, mu naught, is 2600. Well, we need to determine if it's a hypothesis test. What kind of test is this? Has anyone spotted if it's left, right, or two-tailed? Good call. This is absolutely a two-tailed test because it did say, yeah, it almost feels like it should be left tail, right? Because, I mean, the sample's higher, the question's less, but good eye. If they say just strictly differs from, that's the two-tailed test indicator there. Something would have to tell you in the problem very specifically, test if it's less than, we have evidence it's less than 2,600, or evidence that's greater than 2,600. Just the sample being larger didn't give us that direction. Here, they're asking for the two-tailed test. So differs means not equals, so two-tailed. And here's the whole set of instructions. Again, kind of frustrating. Perform a hypothesis test. Provide a practical conclusion using the context. I think on example 1, I forgot to write this in, but it did say use a significance level. Alpha is 0.05. So from here, well, this feels weird just copying in verbatim, but sometimes that just helps build the mental connection with what you see on paper, what you read, and what you're about to use if you just write it down again. Sometimes these are given as a percentage, and it's a good idea to rewrite it as a decimal number because you do use it in decimal form. But here that just seemed kind of like not a big deal writing that in. Okay, so we have quantitative data. We're doing a full hypothesis test. That means it's not going to be too different at all from what we did here. We'll devise a 4-step process. We want parameter, hypotheses, we want a test statistic, a p-value, and then a conclusion. So we're just going to rerun this, except we won't say p equals, we'll say mu equals for quantitative data this time. So here's the 4-step process for this situation if it comes up. Step 1, define the parameter using context. Then state H naught, HA, state the hypotheses, the null and alternative hypothesis. So let's start off with parameter mu. So well, the sample was for 40 cars, and they said the sample mean was 2,752 miles. This is per month per car. To better understand the average number of miles driven per month per car. So that's kind of a complicated unit. Let's say mu is going to be the population mean it'll be a new amount, miles driven per month per car. So that looks like the data along with the unit, but we have to mention the population as well. This is for all cars in the corporate fleet. So we can say for every car in, instead of saying the corporation has a large fleet of company cars, I'll just say for every car in the fleet, letting the rest of the context tell us we mean the fleet of corporate cars when we say that. And, well, there's one more element to this because they told us previous years had the average of 2,600 across all 12 months per month per car. And so this was, well, the current year. So we can say in the current year or for the current year. Whenever the study was conducted, we could imagine 2025, but looks like this is just a made-up scenario, really. There's no actual citation in this anywhere. So I'll just say for the current year, whenever the study was conducted. So in the current year, the average is this amount. Historically, it came out as 2,600. And this is our parameter mu. Does that make sense to everyone, putting all that together so far? Okay, well, let's write out what our hypotheses are. We usually wrote this out as one big sentence, but let's do it differently. It's okay to just slap it down. It doesn't have to be a sentence. You could say, test the null that mu is mu naught, 2,600. We're looking for evidence on the alternative, HA, so let's just write it down. That mu, double check the statement again. It's a two-tailed test, so we're testing if mu is different from 2,600. Sample mean indicates it might be, but keep in mind the standard deviation is pretty large on this one, and that's the other half of the story. And now those are the hypotheses, but it really pays to write down alpha one more time, just to remind ourselves after we get the p-value, we're looking at that number next. You don't have to include it, it's just kind of a safety thing to make sure it's there. So that's step one, it's kind of a big step. We have the parameter, we have the hypotheses. So what makes a good step two? Let's see here. I would say a good step two on this one is to compute, I want to say the standard error for this one. Then after we have the standard error, we'll calculate the test statistic. So I want to keep it in the same order as we did before. Let's say for an overall step two, compute the test statistic T. And the test statistic T on this one is going to be y bar minus mu naught divided by standard error of y bar. I'll keep this as just one step too, so that's same as the 4 steps on the last time we did the hypothesis test. And like before, let's break this down into chunks. Denominator is the only thing we don't have calculated, so let's go SCY bar. Formula, just like the confidence interval we just did, is exactly the same. That's kind of nice. It's S over square root n. So S is the 550 miles divided by square root of 2752. And that gives us the denominator of the test statistic, the so-called standard error. So 550 divided by square root 2752. And to 4 decimal places on this one, I've got at 10.4843. Miles. Unit is not as important, but it's interesting to know that's an approximate standard deviation. So it's in unit of miles as well. It's a standard deviation on how much y bar can vary. So now with this information, we can calculate the test statistic T. So T is going to be equal to, we make 3 substitutions. First, the y bar, we see it on the top of the notes, was, hang on, there is one wild mistake here. So I'm looking for my y bar, and I found it, the 2752. The numbers must have just kind of ran together in my head. But notice the mistake. When I was looking at the sample size n, my brain went to here, should have gone to there. Sample size is 40, not 2752. So let's backtrack a bit on this one. 40 goes there. On the calculator, if you up arrow twice, it's an easy correction to edit and fix. Go inside the square root, hit delete, and then just type in 40. Okay, it's even bigger by quite a lot. Standard deviation is now 86.9626. Miles. Okay, so sorry for that backtrack there. Sometimes these kind of things happen, but we grade on partial credit. So if you mixed up a sample size with the statistic, you might have lost a point here, but just keep on going with the information you have, and you're not going to get double jeopardy on everything else. So let's try this again. We're substituting in value for y bar. Now it's 2752. Subtract. Formula says use mu naught next. That's the hypothesized value, the value to be tested, 2600. You could also spot it. It's going to be the same value in the null and alternative hypothesis every time. Divide by the standard error, 86.9626. And now we just about have that test statistic. So let's go 2752 minus 2600. Divide by, either type that in or use the calculator's copy paste system again. You can up arrow, hit enter to bring that number down. And it comes out as, doesn't look significant. That's not even quite 2 standard deviations. So it's to 4 decimal places, 1.7479. It's a good idea to double check the numbers didn't do a backflip and kind of get transposed. Okay, I think we've got the right value. Step 2 is done. Once we have the test statistic, we'll get the p-value, and that will inform us once and for all exactly what the conclusion is going to look like for this problem. So on to step 3, test statistic. Or excuse me, the p-value. Compute. the p-value. You know, the method here is very important to convey as a method that you use with quantitative data. Because we used mu, because we're using a test statistic t, the data is quantitative. And what that tells us is use TCDF. We use inverse t if it's a confidence interval and we're getting t star. But for quantitative data with a p-value, it's TCDF this time. Either way, it's the t distribution, and the test statistic being called t is a reminder. The critical number t star is the other reminder. So here's what the picture would look like as a quick graph. It's a two-tailed test, so we have to double a p-value on this one. That's one of the tricky things. And, you know, one thing I didn't calculate was degrees of freedom either. So let's make sure we calculate that as well. Let's bake that into step 3. Degrees of freedom is going to be sample size n minus 1, which is a sample size 40 minus 1 for 39. So the reason I need that is that's part of the input to the calculator. This is the T39 distribution. Next, plot your test statistic T. It's a little bit easier to calculate this time. That'd be about 1 standard deviation where the dot is. So 2 standard deviations. Let's go just a little bit shy of that. Puts a value here. So here's our T test statistic. Because the test is two-tailed, there's other area right here. It'll be the same exact symmetric area that we're using, but because we have a number for this value, 1.7479, we can use that number. Well, we have this number as well. It's negative 1.7479, so you could use that number if you'd like. But following the strategy verbatim, like we've done it in class in the last chapters, this is what we're going to do next. That's input 1, lower. This is input 2, upper, equals 10 power 99 because we're shading to the left. Now, next thing before going into the calculator, let's write out that the p-value is going to be 2 times some number that we're going to pick up. And the reason it's 2 times is because, once again, the whole test is two-tailed. So purple trying to highlight in that color is a little bit tricky, but because it's two-tailed, we're going to use that value there. So finally, hit second, bars, go to TCDF. It's all the way down on option 6 for this one. Lower value is the test statistic, 1.7479. Upper is 10 power 99. And degrees of freedom is the value we calculated over here, 39. So hit enter on all that information. And here's what I get. It's not the p-value though. Notice if it was the p-value, that's statistical significance because it's less than alpha. So if they said is greater than, if they indicated a right tail test, we have statistical significance. But we can never switch the data to, switch the test to match the data. They will probably have decided on a two-tailed test before they even calculated the sample mean and sample standard deviation. And they can't switch it at this stage just to get statistical significance. So we're basically locked in. The number we're doubling is 0.0441, or 0.0441, or 2 upon rounding. When your calculator, go times 2 to do the doubling factor. And that's our actual p-value. Twice as big as we might have expected. The p-value this time is 0.0884 upon rounding. Well, any questions at all, folks, getting to that p-value there? Let's compare it against alpha, the significance level. This is greater than or equal to 0.05, which is equal to alpha. So the fact that the p-value is large this time tells us our data of 2,752 miles on average isn't really that different from a hypothesized mean of 2,600 miles on average. This can happen about 8 times out of 100, close to 9 times out of 100, getting data as extreme as this sample mean or even more extreme. So we call that routine, and that means we will fail to reject the null hypothesis H naught, which means our conclusion has to go in a really particular way. We won't say we have significant statistical evidence for the alternative hypothesis. We'll say we failed to find it or we lack that significant statistical evidence. By the way, it goes right back to that alternative. So here's step 4. Give a practical conclusion using the context. So because we failed to reject the null hypothesis, let's start off by saying this study fails to provide significant statistical evidence. This is at the 5% significance level. Alpha is at 0.05. But you know, another significance level could have been 0.10, the 10% significance level. So the level of significance also matters. But just like everything else in the design of the study, once they chose alpha, and they do that before even collecting data when they're being the most ethical, they cannot change it. It's now set in stone. So we don't have significant statistical evidence at the 5% significance level. That, now we just read off what the alternative hypothesis would have said. Starting with mu, look at the definition above. The population mean amount of miles driven per month per car for, I forgot the letter Y up here on the very top. Let me put the red dot by it. For every car in the corporate fleet, I'll just say in the fleet. So that reads out, oh, I forgot, for the current year, let's keep on going. For the current year, okay, now we can say it's different from 2,600 miles. You know, one thing that I would have done if I could backtrack and rewind time, I think it's a good idea to actually put in the units on these, like we mentioned before. Doesn't hurt if you forgot, but putting miles on this reminds you what the context is in the very first place, and it can sometimes make your conclusion flow a little bit better down here. So the unit was 2,600 miles, written that way. We got it, folks. That's our hypothesis test, top to bottom. It works out great as a 4-step process for this. The test statistic being one of the major steps computationally, and the p-value just depending on the type of test you're running. Any last questions or comments at all before we tackle the next one? Yeah, absolutely. Yeah, that's a great statement as well. So let's put this down in the notes just for a quick reference. Let's say in just some weird alternative reality, the data was different. And right here, this is the change we're going to make. And your intuition is absolutely right. If we did reject the null hypothesis, we just changed those couple of words right there. So let's suppose this came out as a 0.0384. Now it's less than alpha, a 0.05, which is equal to alpha, which means we reject H naught. So if it goes this way, we'll say the study provides significant statistical evidence, and then everything else is the same. So yeah, that's a really good observation to make. And also it really helps out our mind on how we write these out, because it's really, that's the whole difference. If it's a small p-value, you have provided the significant evidence. If it's a large p-value, like what actually happened, we've just failed to provide that significant evidence. Other questions at the moment? Okay, I'll leave this here as a screenshot for just a what if scenario, what if the p-value was small kind of situation. And now let's take a look into example 4.
Please scroll back.
Yeah, absolutely.
So let's say you're just removing that.
Exactly, yeah. So the study can either actually provide the significant statistical evidence, that's what we were saying here, but that'll only be if the p-value is less than what alpha is. So yeah, we just make that one small change from what we said here, fails to provide, and then everything else flows exactly the same. Because either conclusion we make, the research question itself is right here, the alternative hypothesis. That's what we want to return back to. So that's what we're addressing, that we either found evidence for this or we didn't, like in this problem, exactly. So it's kind of cool in a way because it means your conclusions really are that close. It's just failing to or not, depending on alpha and the p-value as well. Other questions or comments so far?
And you said that they're only gonna give us, they only overrode you on 2 of these questions, right?
Yeah, exactly.
You just
The
don't know
last
which
two. That's right. Yeah. And that's why we're doing 4 of them, because there will be exactly one hypothesis test and there'll be exactly one confidence interval. But what I'm not allowed to say is the hypothesis test quantitative like this one, or is it categorical like the one above right here? So we've got to be prepared for both. And likewise, I can't tell you for the confidence interval problem, they'll be quantitative like this one, or categorical like this one probably is when we take a look into it. So that's why 2 pages of notes also feels about right. This is a lot of stuff to put on your notes. So one entire page could just be dedicated to this kind of stuff with reminders of what to use in the calculator, how to compute every bit of these elements, like say, for example, the degrees of freedom, the test statistic, the standard error. All these kinds of stuff can change a little bit depending on the scenario. Other questions about that so far? Okay, well, I don't think we have enough time to complete example 4, but we can tear it apart and get started on it, giving us a bit of a head start on tomorrow's review. This one's real data, and it looks like pretty dang serious, heavy situation we're dealing with on this one. It says in the article, prothrombotic factors in children with stroke or porencephalopathy. Not sure I'm pronouncing that right. This is in the Pediatrics Journal. The authors, Lynch, compared differences and similarities in children with arterial ischemic stroke and porencephalopathy. These are pretty crazy words. This is stuff you may not necessarily want to Google unless you have a pretty strong stomach for this kind of medical information. But you know what? The nice thing about statistics is you don't have to be an expert to analyze this. This is messy data. It's pretty chaotic, but that's our job. That's what we've been doing this entire semester is untangling the chaos, running the test. And we don't even have to be an expert on this kind of information to make that happen. We're told next, 3 classification categories were used. Well, that just indicates it's probably categorical data with 3 outcomes, which seems slightly confusing. Perinatal stroke, delayed perinatal stroke, and childhood stroke. Of the 59 children in this sample, let's write out a sample size, 25 were diagnosed with delayed perinatal stroke. So even though there's 3 categories, we can bake this into 2 categories, successes versus failures. And this one seems to be the thing that came up twice. Delayed perinatal stroke. I'm not sure if I'm pronouncing that right once again. That looks like it's the success. And just another reminder, a success in statistics for categorical data is not always a nice thing. This is a pretty awful thing. But we have 25 successes based off this information so far. So data is categorical. We're going to do a confidence interval analysis at a level of 99% confidence. So this tells us C equals 0.99. We'll provide a practical conclusion, and that's the whole statement of the problem so far. Categorical, sample size 59 with 25 successes.
Since our windows can be bigger, right?
Yeah, probably, because that sample size is small, and also the confidence is really large. You're probably looking more into the confidence for the widening.
Yeah.
Yeah, absolutely. That's going to make it pretty wide altogether. So let's get started on this one. If it's success failure data, and we're looking at 3 categories, the failures are going to be perinatal stroke, childhood stroke. The one they want to really study and understand better was delayed perinatal stroke. So this one here. Again, I'm not completely certain what these conditions look like. They sound pretty awful. But this takes us to step 1. This is a confidence interval problem, so we don't need hypotheses. We just need a parameter. So we'll say for step 1, state the parameter using the context. The data is categorical, so don't let me make that mistake again. It's P for the parameter, not mu. P is going to be the population. You can say proportion, but let's change it up a little bit, mainly thinking about the conclusion. I'll put instead of proportion, percent or percentage. So this is going to be the population percentage of, we mentioned the successes, delayed perinatal stroke. Then we mention whatever the population is. I'll say among all. My gut instinct is it's among all children, but let's really look into this. It could be a certain class of children that already have a condition. So this is a good time to reread the context as you're defining the parameter. It says,
Arterial, ischemic.
yeah, good eye.
And porencephaly.
So that looks like the population. We're not looking among all children in the United States of America or in the planet. We're looking with children that already have, as you said, arterial ischemic stroke and porencephaly. So that's the entire population. Let's highlight this in yellow. Let's call this the population. And say among all children with arterial ischemic stroke and porencephaly. I know Usually when you say Ceph like this is talking about the skull in some kind of way. But again, this is not the friendliest data to look into closely unless you have a strong stomach for these kind of medical conditions. But step one is done. We have the parameter using the context. I think we have enough time. Well, no, I might be pushing it a little bit. What is a good step two, by the way? Let's write in some steps and then maybe call it a day just a little bit earlier on this one. I would say a good step two would be find the critical number Z star. And we can do this from scratch in a calculator, just like we did from T star. We would have an area, it'd be 1 minus 0.99 divided by 2. We would do this in the standard normal distribution. But you might have remembered way back in chapter 13, we had a table for this situation. If you go to section 13.3, this might have been on your notes for exam 3. By the way, looking into your exam 1, exam 2, exam 3 notes as you're writing your final exam notes is a great idea, since you'll have a good idea of what you really used for those sections. And here's the table. At the typical levels of confidences, these are the critical number Z stars that will come up. And on the real final exam, we're going to stick to these common confidence levels when it comes to a Z star scenario. So let's paste this in. When it comes up to T star, we do have to calculate that one from scratch. I think this is a good thing to just throw into the notes as a reminder. This is really good stuff to have ready to go. Saves you a lot of time and computation. So when I say find the critical number Z star, here it is. At 99% confidence, Z star is going to be equal to 2.58. Now, if we did it in the calculator, we'd have more decimal places, but that's okay. I'm not going to be as critical rounding on the final exam, like say MyLab statistics would have been. Now, after getting your critical number, step 3, again, kind of going in the same order for the last confidence interval problem, step 3 would be to find the standard error but this is a different standard error. This is for quantitative. Data. The formula for that standard error, we actually haven't used it once yet on this set of notes, the final exam review. We use the standard deviation when we did a hypothesis test, but we don't use that in a confidence interval problem. We don't have a standard deviation. The best thing we have is its approximation, the standard error, and the formula for this one will go square root p hat times 1 minus p hat divide by sample size n. Again, this one is really tricky because if we peek up above for just a moment, when we did the hypothesis test for quantitative data, we did not use a standard error at all. It just felt like it because it seems to have a similar structure, but we used a hypothesized value P naught. This time with our problem, there is no null hypothesis, so we can't grab a value like that.
You scroll up to the last question that we did.
This one over here, or right around here maybe.
Right there. So what is that? Compute the t-tested S standard error of y bar. Isn't that the same thing?
It's different. Yeah, when we say of y bar like this, we're using S divided by square root of n because our data this time was quantitative data.
So scroll down to the left.
Down to this right here.
We have SE of y bar.
Oh yeah, thanks for spotting that. That should have said SE for P hat to make that totally correct. So it has to match the statistic P hat. Thanks for spotting that discrepancy right there. So if there's a P here, should have been a P hat on there. And to tie in the other one, if there's a mu, there should be a Y bar on this one. The mu's and P hats have been a little bit tricky to set of notes, it turns out.
Crazy.
Yeah. When it's all on the table, it gets a little bit jumbled. So thanks for spotting that. Well, we're pretty much at the end of our time, so I felt like just putting the formula down gets us kind of set up for finalizing this problem when we come back next class. But any last questions at all, folks, before we call it a night? Okay, well, when we finish off this one, we're going to go to the second half of notes where it's just kind of random problems from the other chapters we looked into. I want to cherry pick one question because we haven't done a regression analysis in a while, and there is a regression analysis question on the final exam that we should practice for these notes.
Also,
Yeah.
sorry, I don't really have time, but
Oh, you're
you
good.
wrote, find the standard error for quantitative data.
Oh, yeah, this one should have said, maybe that's what gave me that Y bar there. This should have said for categorical. So two weird mistakes. At least they were consistent in a way. So thanks for spotting those. Makes the notes better. This is for categorical data, which is why there's a p hat in that spot. Other questions at the moment? Okay, well, we'll call it a night here, folks. We'll come back on Thursday, do as much work in these set of notes as we can with the remaining time we have. We'll probably solve the next problems a little bit faster because these hypothesis testing confidence interval problems, they're the long ones of the whole semester. But have a great night, folks. We'll be back into this next class.
For example, I have 3 questions. Just
Yeah.
for note state purposes. So example 3 that we just did. So this was a hypothesis value.
Yeah,
So I'm just labeling the top of my notes. Like, so for example 4, I put a confidence interval for categorical data.
yeah,
Correct? So I can reference it quicker. And then so example 3 would have been a hypothesized test.
yeah. Hypothesis test for quantitative. No, that's a good thing to throw in these. Let's actually do that on all of them. I like that strategy. So let's call the first one. This one was hypothesis test.
This is example 1.
Yeah. Example 1 is a hypothesis test for categorical data. Let me put this in something that's going to kind of pop out. Let's go with, red font. No, red font just sounds angry. Let's go for something else. Just highlight that in yellow. That should do the job. So this was hypothesis test for categorical data. Example 2, this one is a confidence interval for quantitative data. And yeah, this is a great strategy for just organizing what things are in your notes. You pick the data type, categorical versus quantitative, figure out the method, hypothesis test versus confidence interval, and then you'll be on your way. It's kind of like a flow chart at this point. Example 3, this one was a hypothesis test. The data is quantitative, so let's call this a hypothesis test for quantitative data. Put that back in yellow. And last one to this here. Oh, sorry about that. Yeah. Typing things out just feels a little bit differently sometimes. So example 3 is hypothesis test for quantitative. And last, example 4 says do a confidence interval, but data is categorical, as that correction shows. So let's call this one confidence interval for categorical data. That's kind of cool how this connects pretty much with chapter 1 of the whole course. You might have been wondering, why do we focus so much on categorical versus quantitative data? And this is the reason, just so we can know what exact tests we're running in the very first place based off the data type. Thanks for mentioning that. That's a great addition to the review notes. Other questions at the moment?
I was writing the same thing, so I'm glad you asked.
Yeah, me too. I'll probably do that next time I teach this class as well. Put in this big marker there. Well, have a great night, folks.
Yes, well, I've made my notes. And I was looking at it, because all I did was shrink down all my notes
Yeah.
on that. So it's a lot of little words on my note sheet.
Yeah, you need something big to kind of zero your eyes in to
Bring
the
it
right
magnifying
quadrant
glass.
of it. Yeah. Magnifying glass is fine. It's kind of like eyewear, so
Bring them, those aren't against the rules.
not at all. Yeah, that'd work out just fine.
Thank you, have a good night.
You too. Take care. Yep. Have a good one.